Hello everybody, this is a quick video on the square root function, or the inverse square function as some people call it. But I had a student ask me about how to graph these things. So specifically we're going to take a graphical approach to these today. And so just to get started, I'm going to kind of bring up what we mean by the inverse square function. Or the square root function. Let's go ahead and take a look at what we've got here, which is y equals f of x, or I like function notation, so f of x. But f of x equals the square root of x, and the best way to kind of explore any function is to start by maybe graphing some solution points for this. So as you can see, I haven't written on my Bamboo in a while, and I'm not doing a very good job of it, but we'll call this f of x. And so I think, a good place to start is the fact that, if we tried to plug in some negatives here, we're going to get some undefined values. And so what we're really only looking for here are positive, not positive, but real solutions and non-complex or non-imaginary solutions. So right off the bat, for example, if we tried to plug in -2 here, we would get f of x would be the square root of -2, which, as everybody knows, is just plus or minus I radical 2. And so since that's not what we desire, I just wanted to bring up the fact that plugging in negatives not going to get us very far with this function here. So we'd say here, and we could just chalk this up to being non-real, these two solution pairs. So like whatever, I don't have anything against complex numbers, it's just that these two, they aren't going to be graphed very well in the xy coordinate plane. So starting with 0, we say square root of 0, of course, is 0, so we get a point starting at the origin. That's kind of an important thing to note here, is that it starts at the origin. We say we plug in 1. The interesting thing is we say the square root of 1. And so for the first part of this, I'm going to argue that it's actually plus or minus 1. And the reason why is because, hey, I could take -1 times itself and still obtain this 1 right here. And so maybe instead of this 2 right here, we should probably go with 4 since we're taking square roots. So we say, okay, so if we plug that in, we get square root of 4 plus or minus 2. And so graphing this, let's go ahead and take a look. We've got, all right, crooked y-axis, and of course our somewhat straight x-axis here. And graphing this, we'll go ahead and throw in our x values that we plugged in, starting with 0. So when we plugged in 0, we got an x value of 0. That's right, boys and girls, we went through the origin. When we plugged in x is 1, we got a y value of 1. And then when we plugged in x is 4, for the sake of convenience, so we had 4, here's 5. 4, we got a y value of 2. And so when we graph this, what you start to see is just this. It's kind of, if you want to think about it this way, I called it the inverse square function. The reason why is because it's kind of like a halfway parabola here. Now, the interesting thing is, you notice this is half of the parabola. Where's the other half? Well, remember when I said square root of 1, I said it was both positive 1 and negative 1. That is, an input of an x value of 1 went to both positive 1, but it actually also proceeds down to -1. And an input of 4 actually got us plus or minus 2, so an output of positive 2, but also -2. And so in essence, we would have this other side of our sideways parabola here. It's just that if we attempted to do this, the weird thing is that this does not pass the one-to-one or vertical line test. That is, we have several x values proceeding to more than one output. So what we tend to do with the square root function is we like to, let me undo all this here, so we get back to our half parabola. Awesome. We like to restrict the output and say that all roots we will consider to be positive. And only for the sake of convenience, look, in some other alternate universe, we might say that all roots are negative, and we'd have this little sideways parabola down here and ignore the top half. But the reason why we ignore the negative outputs is because if we restrict it to positive outputs only, then this would necessarily pass the vertical line test for being a function, and that's what we like to see in inverse functions. This is the inverse square function, and we'll take a look at y here in just a second as we click over to GeoGebra. Okay, so this will be a nice little outlet tool for us to graph these things. It'll save us some time. But let's start with our basic function here. F of x equals square root of x. And so you'll notice here we've got our half parabola. Starts at 0, 0, and it goes up through the point 1, 1. So that's kind of a point I like to remember. We've got this output here, and we could see actually this whole parabola simply by saying, what if we graphed g of x, another function, and we'll make this the negative square root of x. We would actually see the other half of that parabola. And just to kind of go to show that this is the inverse of the squaring function, which is, we'll call this, let's see, we've got a g of x. We'll call this h of x. The squaring function would be y equals x to the second power, which is our basic parabola that also starts at 0, 0, as you can see, and goes through 1, 1. It's just that these lines, of course, since they are inverses, are reflected about the line y equals x, okay? So much that you probably didn't want to know. You're probably saying, I'm watching this video because I want to know how to graph these things. So let's go ahead and start with our primary graph here, which is, you can see I was already graphing some, y equals the square root of x. So the question at hand is, how do I graph these things? So let's click back over to Photoshop here. There are a few elements I'm going to point out here, and this is very specific to square root functions, and I'm very sorry. We say, in general, we say it's a times the quantity x minus h. We can totally associate those with parentheses, plus k. And so some quantities I want to notice here are a value, h value, and k value as we work through these, but what effects they have on the graph of the original y equals the square root of x. I think that every graph that's a square root function kind of looks like this original graph, just maybe a little bit more transformed. So going back over to GeoGebra, the nice thing is I have already graphed square root of x. We'll graph another function, g of x equals dun, da, 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 square root of x. It's the same thing. But the nice thing is I can highlight g of x, and I'm going to start scrolling up. Okay, and really what I'm doing is transforming my graph so that it shifts vertically. So you see I'm kind of moving this around here. Maybe I'll have this one start at, I hope you can see this, 0, 2, as opposed to 0, 0 like the original graph. But what you notice about the function over here, my mouse is up here in the top left here, is that f of x is equal to the square root of x, but this graph, it started at 0, 2, that was shifted twice or 2 units up from the original starting point, was the function g of x equals the square root of x plus 2. So I think, you know, one might surmise this 2 has everything to do with that. You'll notice as I scroll up and down that value is actually changing. So, you know, this, if you think about it here, the square root of x plus or minus this number off to the side, going back over to here, this kind of correlates to this k value here, okay? And so what we're going to do is we're necessarily going to imply that k has everything to do with what we're going to call vertical translation. Vertical translation. So that k value tells us what's going to happen in terms of shifting our original graph of y equals square root of x up and down. So, you know, one might necessarily assume that h is going to do something similar. So let's kind of mess around with h. And it's kind of fitting that we use the letter h here, because what if I bring that g of x back down to the square root of x so that they match up on top of each other and start shifting left and right. Now again, I don't know if anybody can notice here, this is the whole point. I want you to notice right up here, but we have this time the square root of x plus 2, but you notice that plus 2 is inside the radicand with our x and not on the external portion of the radical. So we say the effect that this caused to happen was this new graph that's being bolded here, g of x, is kind of like the original graph of square root of x. Everything is the same except for one thing, it starts left 2. So the interesting thing to notice about the h value here is that it's, you know, it's considered backwards. And I don't want to say considered backwards because it's actually not. But the way we write the formula, if you notice here, was on the inside here, x minus h. And because of this negative right here, we tend to think that h is backwards of what it normally is, okay? So, you know, saying I shifted my graph left 2 caused us to have a plus 2 on the inside of here, whereas if I would have started at maybe right 2 from the original, it would have been a minus 2 in there. So let's go ahead and write down what we have discovered here. I'm trying to make this a little bit quick. We say the h value has to deal with horizontal translation. And an important thing to note here is that it is backwards. So if it says plus 2, it means it really shifts left 2. And so now on to this a value business, and then we'll kind of get into our second video here. So what does a do? What is this number I'm multiplying by my square root function or my inverse square function? So again, we will mess with, say, g of x here. Why not just delete g of x? Delete. And we'll throw in a different g of x. And except this time we'll call g of x equal to 2 times the square root of x. So now we've got a situation in which, and maybe I can manipulate our graph here. Here's our half problem, where it's kind of stretched vertically. So we say, really, what's the difference? Well, because 2 times the square root of x here, it doesn't have anything added or subtracted from the x on the inside, nor added or subtracted from x or the square root on the outside. It's not going to be vertically shifted or horizontally shifted. You notice that both of these graphs still start at 0, 0. It's just that where on the original, we say the a value was 1 out front. We didn't write it, but it was 1. If you can kind of maybe think of that as a slope, remember slope is rise over run. Now I am not advocating that this is a slope, but if you look at that a value in terms of a rise over run, we notice that both of these graphs start at the origin, but the first graph kind of went up 1 over 1 and went through this point 1, 1 to get to its next point, we can kind of draw the rest of the half parabola through that. Whereas the second graph from 0, 0 went up 2 over 1. You know, the a value is 2. That's 2 over 1. It's not a slope, but if we look at it as kind of interpreting it as a differential there, we could say that a value really helps us to go from our original point 0, 0 to the next point, or our starting point to the next point. So if that's the case, then we could hypothesize if we put in some new function h of x, and we call this half square root of x, or 0.5 square root x. I want you to consider that 0.5, if we turn that into a fraction, that'd be 0.5 over 1. But this graph from 0, 0 should go up 1/2 and over 1, and you see that it actually does. From 0, 0 it goes up 1 over, or up 1/2 and over 1. It's at the point 1 comma half, okay, and then proceeds to go on through there. So a what we want to indicate is that a is kind of like vertical, we say vertical stretch. Okay, so the larger it is in magnitude, then we say the more vertically stretched it is, and the smaller it is in magnitude, the less vertically stretched. Okay, so we'll go ahead and move on to the second video now.